So today's class what we will do is we will look at a one-sided derivative for the first derivative representation, right, and then we will look at again, we will go back look at the second derivative, and if we have time we will go on to applying it to a set of simple problems, because by the time we are finished here we will know how to represent functions, we know how to represent derivatives, so we might as well try out a few simple problems to see if we are able to solve differential equations that are of interest to us. Okay, fine, is that okay? Right, so if we want second order, meaning truncation error is second order, first derivative, this is what we want, right. In the last class, as I said, I have already done a higher order. Let us look for a second order. So if I have the points I plus 1, I plus 2, these are located at xi plus 1, xi plus 2. The function values there are fi plus 1, fi plus 2, and right now first what we will do is we will assume that h is like h in fact equals xi plus 1 minus xi, which equals xi minus 1. We will assume that they are equal intervals right now, okay, and later we will do unequal intervals, because unequal intervals are of interest to us, though except here you will see it here in this class and then you will never see me use unequal intervals again. So this class is important in that sense, unequal intervals are important, but for this course I am not going to do unequal intervals outside this class, okay, is that fine? Okay, so it is a simple game now, so now we are going to do it right clean from the start, simple game now. We want to find the derivative at I, and I am going to use the points I plus 1 and I plus 2, we will use Taylor's series. So f at I plus 1 is f at I plus h times f prime at I, the prime indicates differentiation with respect to x, plus h squared by 2 factorial f double prime at I plus h cube by 3 factorial f triple prime at I plus h to the 4th by 4 factorial f fourth derivative at I, and then so on, okay. In a similar fashion fi plus 2 is fi minus h times f prime at I am sorry plus 2h times f prime at I. You can see in my mind I did an I minus 1, it is okay, you have to be very careful, okay, fine, plus 4h squared by 2 factorial f double prime at I plus 8h cubed by 3 factorial f triple prime at I. The reason why I do not succumb to the temptation to expand this out and cancel and so on is because I know I am going to combine these two terms, right. So I leave whatever is common between them, I leave them as they are, okay. There is a temptation when you are writing this to cancel terms and so on, do not do it, plus 16h to the 4th by 4 factorial, the 4th derivative, and so on. So we look at these two, our objective is to extract out the f prime at I. So what do I need to do? If I multiply the first equation by 4, I will get a 4h squared here and I will get a 4h squared here. So if I multiply the first equation by 4 and subtract the second equation, I will knock out the h squared term. So 4 fi plus 1 minus fi plus 2 is 4 fi minus fi, which is 3 fi, 4h f prime, right, minus 2, that is plus 2h f prime at I. This will cancel, that is the whole point of multiplying by 4, and this gives me minus 4h cubed by 3 factorial, the third derivative, minus 12h cubed by 4 factorial, fourth derivative. Did I make a mistake? H power 4 by and so on. Okay. So it is very clear, it is very easy to make mistakes, you have to be really careful when you are doing this. Fine. So let us solve for f prime at I. So if we come here and you solve for f prime at I, that derivative is 4fi plus 1 minus 3fi minus fi plus 2 divided by 2h, and what does that leave me? 2h squared by 3 factorial f double prime plus higher order terms, f triple prime plus higher order terms. So if I throw this out, I say this is the representation for the derivative, I throw this out, right. So this is the truncation error. Truncation error is of the order of h squared, so it is 1 by 3 h squared f triple prime at I. Is that fine? Truncation error is of that order. And again, like I did last time, I make a quick check, I add 4 minus 3 plus minus 1, that is 0. Why do I say that? You ask yourself the question, why do I test? Even last time I tested by adding up all the coefficients to make sure they added up to 0. Why do I do that? Constant function, it should work, yes, constant function it should work. It should work for a constant function, it should give me a 0, right. For constant function it should give me 0, and of course in the limiting process, the numerator is supposed to go to f at I. If I actually take the limit, remember this is a finite difference, if I go back to the infinite process, which means I take the limit h going to 0, right, the numerator is supposed to independently go to 0 and the denominator goes independently to 0. It is the ratio that gives me the derivative, you understand, right. So from a, how should I put it, from a operational point of view, yes, I have a derivative, I have a representation for the derivative, and the constant function should give me a 0 derivative, right, that is from an operational point of view. The other processes, of course I have an infinite process for which I have replaced by a finite, I stop, I do not divide by, I do not take the limit h going to 0, but if I do go take h going to 0, this should go to the derivative, it has to converge to the derivative, right, we want it to converge to the derivative, is that clear? Okay. So the summation, so that is one sanity check that you can always do, add to make sure that they all add up to 0. Okay, this is fine. Now what if they were unequal intervals? What if they were unequal intervals? So we have these weights, we have seen this is very nice, we have the truncation error, but what if the intervals were unequal intervals? What if the intervals were unequal intervals? And just for the fun of it, we can do we can still do a comparison, but just for the fun of it, we will do I minus 1 and I minus 2, okay, and in this case this length happens to be h, and to keep our algebra simple I will call this some alpha times h, is that fine, just to keep our algebra simple, and this kind of a relationship you may actually get in future applications. So I will leave this as alpha times h, and we will just quickly repeat this process, okay, we will just quickly repeat this process. So what do we have? F at I minus 1 is f at I minus h times f prime at I plus h squared by 2 factorial, second derivative at I, minus h cubed by 3 factorial f triple prime at I plus h to the 4th by 4 factorial, the fourth derivative at I. and so on. F at I minus 2 is f at I minus, I am sorry, 1 plus alpha times h f prime at I plus 1 plus alpha squared, 1 plus alpha whole squared, h squared by 2 factorial f the second derivative I. So it is very clear, it is not that bad. Plus so on, right, 1 plus alpha power 4 factorial h to the 4th, and that will be multiplying the 4th derivative, and you have all the other terms. What do I do now?
Square.
So if I multiply the first equation by 1 plus alpha squared, if I multiply the first equation by 1 plus alpha squared, I should be able to cancel out the second derivative term. Okay. So 1 plus alpha squared fi minus 1, 1 plus alpha squared fi minus 1 minus, I am going to subtract out this term, fi minus 2 equals, so you should be happy if alpha over 1 plus alpha squared is 2 squared, which is 4, which is what we did earlier, right. So that is not bad. fi minus 2 equals, we have 1 plus alpha squared, oh I keep doing that, minus 1 fi what happens to this term? So you get 1 plus alpha squared minus 1 plus alpha h f prime and what else? Minus alpha, no by 2, no by 2, that is the first derivative term. Then what is the third term?
X cube by 3 factorial.
The third term goes away, so and then you get minus 1 plus alpha squared minus 1 plus alpha cubed. H cube by 3 factorial f triple prime, and I will not bother with the fourth term, right. The fourth term is something that you can work out, because normally when I do it, when I am sitting alone, I sort of simplify this a little faster than this, right. So but it is fine, we will let us see what we get here. So we have 1 plus alpha squared fi minus 1 minus fi minus 2 equals alpha into 2 plus alpha, is that fine? And if alpha equals 1, that gives you 3, so we are happy, it is working out, so that is fi, okay. And what is the next term? I can factor out 1 plus alpha, so that gives me a minus 1 plus alpha into alpha h f prime at I, and alpha equals 1, that is 2, okay, that also works, plus plus or minus 1 plus alpha squared into 1 minus alpha h cubed by 3 factorial f triple prime I and so on. Okay, actually I made a mistake here, there is a 3 factorial at that point, it is okay. Is that okay? So what does it give me for f prime at I? One plus alpha squared minus alpha 2 plus alpha fi minus 1 fi minus fi minus 2 divided by alpha into 1 plus alpha. Do you have a sign problem? There should be a negative sign here, okay. And this, what is the truncation error now? Minus alpha into 1 plus alpha squared h squared by 3 factorial, and I have to divide by alpha times 1 plus alpha, so that gives you an 1 plus alpha f triple prime at I. It has to be a plus. No, it is right. There is a negative sign here, there is a negative sign here. Where did I miss? There is a negative sign here, there is a negative sign here, and there is one more negative sign. It will turn out right. See, I have another way by which I checked. If you notice, I glanced at the other board. What was the truncation error for the forward difference? That was positive. So this will be negative, right? There are some simple sanity checks that you can do, fine, okay. So, and you can see if you set alpha equals 1, whether it works out. So clearly if they are unequal, it is going to become very messy. Yes.
Approximation, if you take the next point, then we can use the previous function value just as it is. Suppose I have, now I am doing I, and I go to I plus 1, I can still use I plus 2 as it is. But if I take unequal intervals, if I go to the next value, I won't be able to use this value, the previous value at the same point, it will be some other value. So if I go to I plus 1 there, I can use I, but I won't be able to use I minus 1.
You use I, but you won't be able to use I. I am not sure I understand the question.
You have to have more function values than.
No, you have, it is the same thing. You have 3 points. They are unequal. They are unequal distances, but I can still eliminate. I can still eliminate the second derivative term and get an expression for the first derivative, leaving a truncation error which has only the third derivative term.
Suppose I want to calculate the derivative at the next point also.
You want to calculate the derivative at the next point, and that could be, it could be some beta h or something of that. So that could be something else altogether. You would still have unequal intervals. You could still have unequal intervals. No, it need not always be alpha. It need not be always be alpha. There is a process called geometric stretching where it is always alpha, right? It is a constant. That is a nice situation. But if it is not, it need not always be the same. Okay. So the point next to it could be some ratio. Is that fine? Right? It need not be h by alpha or something of that sort. It need not be that way. Okay. Right. So the idea is that the adjacent intervals are not of equal size. Fine. So, and as you can see from the fact that the expression is so messy, it is possible for us to calculate it, but clearly from a classroom point of view, right, it doesn't add anything. I just want you to have an awareness. I will do one more. I will do one more in this class with unequal intervals as I said, but it does not add anything to my class as such, right. So if you take uneven intervals, which you very often will be forced for other reasons, right, to take uneven intervals, when you are forced to take uneven intervals, you will get messy expressions, and this error seems to be slightly large. I mean, if alpha is depending on the value of alpha, the magnitude of this error term is going to change, okay. So you should have a reason, so you will be changing these h values because you have maybe possibly some knowledge on how the function is varying, right, and then that is the reason why you are trying to compensate. If you know that f triple prime is large, then you may be changing your alpha in order to compensate for that error, it is possible, okay. There are many reasons. You will see that when you run into it at a later date in a more advanced course, you will see why you would take unequal intervals. In this class, as I said, I will do it one more time, but the reason why I will not persist, I will always assume equal intervals, is because it just makes life easier, and the derivations are always possible. Whatever I do with equal intervals, you can repeat as I have indicated with unequal intervals. Is that fine? Okay. So let us look at the second derivative, right. So far we have looked at the first derivative. You have a first order forward difference representation, backward difference representation, second order forward difference, backward difference, right. You have one third order representation that I did in the last class. So you can work out other higher order. I would strongly recommend that you work out other higher order representations for the first derivative, okay, for the first derivative. Now let us look at the second derivative again. I will repeat the second derivative, I will quickly repeat the second derivative, right, that we did last time. So it is second order second derivative, just because I am going to do it twice, one which we did last class, and then I am going to repeat it again with unequal intervals. So like I did, I have xi plus 1, xi minus xi plus I am sorry, xi minus 1, xi plus 1, I minus 1, I plus 1. Of course you can also see whether you can get one sided derivatives, right, for the second derivative, one sided representations. I leave that to you. So what we have is simple expansion again using Taylor series about the point I, fi plus h times f prime at I, and again h equals xi plus 1 minus xi equals xi minus 1, okay. In this case they are equal, plus h squared by 2 factorial second derivative of I plus h cubed by 3 factorial third derivative at I plus h to the 4th by 4 factorial and so on. Please remember, so we are using Taylor series to expand about the point I, xi, okay. You could as well use Taylor series to expand about any other point. We choose to expand about the point I because we want the representation at the point I, right. We want the representation of the derivative at point I, therefore we choose I. If you want the representation elsewhere, then you have to expand about that point. Is that fine? Is that okay? So f at I minus 1 is f at I minus h times f prime at I plus h squared by 2 factorial f double prime at I minus h cubed by 3 factorial. So this is sort of a dreary process, but unfortunately you have to get it right, okay, otherwise it does not work. The detail is very important. So if I just add the two, this cancels, that cancels. So it gives me, for my first derivative, an expression we derived in the last class. The second derivative, an expression we derived in the last class, that is f double prime at I is fi plus 1 minus 2 fi plus fi minus 1 divided by h squared minus h squared by, there are two of them, okay. This is a truncation error, we have seen this. We have seen this. So the question is, what happens if we take unequal intervals? Okay, we will look at that, and then I will we will close the subject of what happens with unequal intervals. So what happens if you take unequal intervals for the representation of the second derivative? We have seen what happens for the first derivative. First derivative, we still got a second order representation. It is just that the coefficient of that truncation term change. We will see what happens here. So instead of h, right, instead of h, so okay, we'll just write it again. So we have I minus 1, I plus 1, this is h, this is alpha h. Okay, just to keep it clean, we'll just redo it quickly. So fi plus 1 is fi plus h times the first derivative plus h squared by 2 second derivative, which is what we want, plus h cube by 3 factorial the third derivative plus h to the fourth by 4 factorial fourth derivative, and so on. Okay, normally if you didn't know how many you would take a lot of terms depending on what is it, what order you are going to take, right. You can't stop at fourth derivative if you want a much higher order. So I stop at fourth derivative because I know I am going to get something that is of the order of second order. Fi minus 1 is fi plus minus alpha h f prime at I plus alpha squared h by 2 f double prime at I minus alpha cubed h by 3 factorial f triple prime at I plus alpha to the fourth, this is not as bad as the first derivative term, right, h to the fourth 4 factorial fourth derivative at I, and so on. Is that fine? H squared, h cubed, I am being a little careless today. So if I multiply by the, see now I am a little desperate, I want to get rid of that, I have to get rid of that first derivative, that is my need, I want the second derivative. So I multiply the first equation by alpha to get rid of that. Okay, so I get alpha fi plus 1, and to that I add the second equation fi minus 1 equals 1 plus alpha times fi, I get an alpha fi plus 1 fi, the second term cancels, what happens here, plus alpha 1 plus alpha into 1 plus alpha h squared by 2 f double prime at I, that is the term that I want, plus alpha into and what happens to the last one? Now this looks very different, this looks very different. So if I do, if I try to evaluate, maybe write it here, pardon me. No, I think you can verify, you can check it out, it's okay. I get it out of the way now. We'll stick with this material, what we are doing right now. So f double prime at I is alpha fi plus 1 minus 1 plus alpha fi plus fi minus 1 divided by alpha into 1 plus alpha h squared to 2, right. So, if alpha equals 1, that 2 and this 1 plus alpha will cancel, that is the idea, okay, and alpha equals 1, this will be 1, that is 2, that is 1, it goes back to the standard expression. What about the truncation error? So, you have a third derivative term, right. So, you have a minus, this is a truncation error. So, I have divided by alpha 1 plus alpha, so it gives me a 1 minus alpha h by 3 at I, and this gives me a minus 1 minus alpha plus alpha squared, a little algebraic fourth derivative at I, and there is an h squared here, and this is the difference. So, for the second derivative term, if you take unequal grids, the convergence rate drops, the representation of the derivative suddenly became, the truncation error became first order, the convergence is linear, it is not quadratic, it goes to 0 as h, not as h squared. This is very important to remember, and it introduces a third derivative term. This will have significance later on, later in the semester I will remind you about this, okay, later in the semester I will remind you about this. It adds, so if you have unequal grids, it introduces a third derivative term, is that fine, okay, and it introduces a convergence which is first order and not something that is second order. Of course, if alpha equals 1, this goes away, right, and we retrieve what we had for equal intervals, is that fine, okay. So, as I said, it is always possible for us with unequal intervals to calculate derivatives, it is always possible. So, when you encounter it, you know how to do it, but we are not going to do it anymore because it is just a mess and it does not add anything else, okay. But I do want you to remember, this is very important, that if you go for unequal intervals, you cannot be sure that the order that you get is the same order, you have to recalculate it, you have to rework it, okay. Right, now let us apply this, now that we have all these derivatives that we can represent and functions that we can represent, let us apply these, let us apply what we have got, right, to differential equations, some differential equations. We will choose a simple one right now. We will look at Laplace's equation. We will look at Laplace's equation, is that fine, okay. So, we will look at Laplace's equation in 2 dimensions, I am going to stick to 2 dimensions here. So, this symbol is called nabla, right, we are used to calling it del, but it is called nabla. So, this would be nabla squared phi equals 0, okay, fine, and we could choose to solve this problem in a very simple region. We can choose a region that is in the first quadrant, maybe a unit square, and in this unit square you have this equation that is valid, and on the boundary possibly we provide boundary conditions. So, you know of many ways by which you can solve this equation, possibly in PD you have studied variable, separable and so on, right, there are many ways by which you can solve it. Here we look at, see whether we can represent the derivatives on a mesh and whether we can use that to infer the solution, okay. So, to obtain that solution. So, we know that in 2 dimensions this would be dou squared phi dou x squared plus dou squared phi dou y squared equals 0. I will use an alternative notation, I may switch between them depending on convenience. So, if there is no confusion you may occasionally see me write that because it is much more compact notation. Okay, both of them represent Laplace's equation in 2 dimensions, and this is an expansion of that nabla squared. So what is the typical mesh point that I am going to take? Just like we said I plus 1, I minus 1, how are we going to do it in 2 dimensions? In 2 dimensions, in Cartesian coordinates, I am going to take equal intervals, right. So this would have now 2 indices, one for traversing along in the x direction and one for traversing along in the y direction. So that would be I plus 1 j, that would be I minus 1 j, that would be I j minus 1, and that would be I j plus 1. Okay. I will take all of these intervals for the sake of convenience to be h. I think you can figure out what will happen if you change the values. There are so many different things that could happen. It could be h here and it could be some different value in the y direction. Each one of them can be different. There are so many possibilities. You can work it out. So what is the first derivative? What is the first term at the point ij using the expression that we have just derived? It is phi I plus 1 j minus 2 phi I j plus phi I minus 1 j divided by h squared. Okay. So at the nodal points, if I have the function phi given by I plus 1 j, I j, I minus 1 j, phi at the appropriate points, I can estimate the derivative, okay, and we have a truncation error associated with it. I say equals at this point, but we know already that I say equals, but we know it is an approximation, it is a representation, right, but I will write equals ij in a similar fashion is phi I j plus 1 minus 2 phi I j plus phi I j minus 1 divided by h squared. Clearly if they were delta x and delta y, it would be delta x squared and delta y squared, okay, that is not a big deal, fine. So now to represent Laplace equation at that point, so now I am talking about so far we are talking about derivatives, now I am going to actually represent the equation. I will add these two, okay, I will add the two and I can actually represent Laplace's equation xx plus phi yy at the point ij gives me phi ij, phi I plus 1 j minus 2 phi ij plus phi I minus 1 j by h squared plus phi ij plus 1, not a big deal, minus 2 phi ij plus phi ij minus 1 by h squared, and this is supposed to be 0. This at that point is supposed to be 0 at that point, okay. So now I will say this represents Laplace's equation at that point, at the point ij, and it is actually possible for us, to solve for phi at ij. After all, that is really what we want the phi at ij. In fact, turns out, so if you multiply through by h squared, the right hand side is 0, so the h squared will go away, okay. This turns out to be phi I plus 1 j plus phi I minus 1 j plus phi I j plus 1 plus phi I j minus 1 by 4, right, by 4. You could write by 4, just to encourage you to multiply instead of divide, I will write times 0.25. So now I change to a programming notation, multiplied by 0.25, okay, is that fine? But the by 4 is important, it is the average of the neighbors, that is the key. So solution to this equation is the average of solution to this equation at this point the value at this point is the average of the values at the neighboring point. Okay, is that fine? Okay, so now we have some mechanism by which we can represent Laplace's equation at a given point. We will see what we can do with this. Yeah, you have a question.
How does the Taylor series of
How does, well, in this case it does not matter because we are taking derivatives only with x and y, but you can actually write Taylor series in 2 dimensions. There is a Taylor series expansion for 2 dimensions. So if you say, you may have seen it in multivariate calculus, you can actually write it. You can actually expand about the point f of x y, right, and then it will turn out to be, I am just writing this fx fy, where fx is derivative with respect to x, fy is derivative with respect, and you can go on. So you will get h squared fxx, g squared fyy, 2 hg fxy. You understand, and you can keep on adding terms, right. So there is from your multivariate calculus, if you go back, you will look, you will see that you will actually pick up. Okay, so and you would need that if these grids were not orthogonal to each other. That is, if you had grids that were not only unequal, but they are not along the coordinate lines. They are not along the coordinate lines. So not only are they could be equal or unequal, but they are not along coordinate lines, right? And then you can run into this problem that you would have to do it this way. But trust me, there are better ways by which one can do this, right? So we will see, if we will see. I don't know whether you need to look up a little tensor calculus. I usually do something on tensor calculus. We will see whether we get there or not. At least I will give you a motivation for why you should learn tensor calculus as we go along. Okay, let us get back here. What do we have? So this is a problem that we want to solve. We will make up a problem and we will see how we will go about solving it using what we have just derived. So what we do is, again, to keep life easy, we will break this up. We will break up our problem domain using a mesh, and you will notice that in this case, of course, there are 1, 2, 3, 4, 5 at the 3 interior points, right. So this would be, so that would be some point ij that I was talking about, okay. And how would the problem be normally prescribed? How would you normally prescribe the problem? So just say this is a unit square. So this is a point 0, 0, which is the origin. This is a point 1, 1, right. So unit square located at the origin, and what we want to do is we want to see whether we can solve Laplace's equation. So given some boundary conditions, we will figure out how to get those boundary conditions. Given some boundary conditions, if I prescribe some boundary conditions, which means that the values at these points are known. So if I prescribe some boundary conditions, the values at these points are known, and if we are able to find the values at the interior points, right, then we have Fij's at the interior points, and using possibly hat functions or something of that sort, we may be able to interpolate, right. Actually we would use hat functions in 2D, but I have not defined hat functions in 2D, but you can use hat functions and actually use linear interpolants to find a value anywhere in between, okay. Is that fine? So what you can do now is at any given point ij, you just repeat this. So phi ij is phi I plus 1j, phi I minus 1j, phi I j plus 1, phi I j minus 1. I am going to say divided by 4 here, but you know you have to multiply by 0.25. You just repeat this process for every interior node. The conditions on the boundary are given, okay. So when you are trying to figure out what is the value at that node, this is known, that is known, right. Let us number these. So let us say this point is 0, 0, this is 1 0, 2 0, 3 0, 4 0. Okay. So this is 0 1 and this would be 1 1, get rid of that, 2 1 and so on, and this point is of interest. This is 0 2, this is 1 2. So if you want to find the value at 1 1, you need the values at 1 2, 2 1, 0 1, 1 0. From the boundary conditions you have the values at 1 0 and 0 1. Okay, we do not have the values at 1 2 and 2 1. So we not only do not have the value at 1 1, we do not have the values anywhere in between. So in order to get this working, the process that we will start doing is we will make an assumption about the interior values. Just make an assumption. Let us start with a guess, right? A good guess would be 0. We have nothing to go with right now, right? There are many possible guesses. Right now I have not even told you what the boundary conditions are. So good guess is 0. So let us just assume that all the interior values are 0 and you are given boundary conditions. Okay. So you can find phi ij at any given point by taking the values of the neighboring point. Then you can go to the adjacent point, take the values of the neighboring point, you understand, and you can do this for all the interior points. You do not touch the boundary points because the boundary points are known already. So if you keep repeating this process for all the interior points, as time progresses we hope that the phi ij's evolve, that you are generating a sequence of phi ij's. So if this is, you are generating a sequence of phi ij's, right, n equals 1, n equals 2, n equals 3, n equals 4, that you generate a sequence of phi ij's and you hope that sequence converges. Right now we hope that sequence converges, and if that sequence converges you will have a set of phi values at every grid point. Okay, is that fine? Okay. So it's better if you just try it out and work a problem, and I think then it will work out. If you go through that sequence and it has converged, how do you know the answer that you have got is the right answer? Well, you have points at these values, you have grid points. So when you say something is a solution to a differential equation, what do? You substitute into the differential equation and verify whether it is true or not, right. So you could substitute into the original differential equation phi xx plus phi yy equals 0, but in this case you just have points at various nodes, okay, right, and if you substitute in the difference equation you can find out what is it that the difference equation gives you, okay, but the differential equation itself requires that you take derivatives and you have only discrete nodes, okay, is that fine, right. So I think what you do is you can try this out, just give some arbitrary boundary conditions. We will work out maybe a more specific problem in the next class. Just try to give it some arbitrary boundary conditions and see what it works, what happens, right. Yeah.
Sir, we have 9 unknown grid points.
Right. In this what I have drawn, you have 9 unknowns, right.
So we have 9 conditions.
Right.
So we can solve the linear set of equations.
Yeah, there are issues. So that is that we will get to that, right. So we will see what it is that we are doing. That is actually what we are doing, right. We will actually figure out what is it that we are exactly, what exactly are we doing, okay, right. So we will get back to this on Monday. Thank you.